Hi, all. Greetings for everyone. Today, I'm going to explain about a few of supervised learning algorithms, which comes under the machine learning part. Which is actually apart from the core fundamental algorithms, few four algorithms I have choose. It is a little bit useful for our model building. So let's begin. So in supervised learning algorithms. So you have plenty of algorithms from linear models, linear and quadratic discriminant analysis, kernel ridge regression to neural networks. So in this algorithm, there are the core fundamental industry standard algorithms we have to know as linear regression, logistic regression, polynomial regression, support vector mission, KNN, Navy bias, decision tree, and ensemble methods. So these are the most fundamental algorithms which will be repeatedly most used in the model development and all. So apart from that, we have all algorithms. We can try it out. But so here I just explained four algorithms, which is important apart from the core fundamental algorithms. So let me begin. So first, we are going to see about the ridge regression algorithm. So which is actually a regularization technique. So which is used to prevent the overfitting and handles the linearity. So what is overfitting? So we know that when a model performs well in the training set but performs poorly in the testing set, so then we can say that model is not learning, it is memorizing the things and also performing poorly. So in that cases we say it as the overfitting, our model is overfitting. So in order to prevent that case, and also multicollinearity. So what is multicollinearity? So let me explain with the example image here. So here you can see in the first image, so which is actually the low correlation and the no multicollinearity data. Here, so the points are scattered enough, and we can say that there is no relationship between the variables or the features. But in the second image, so the points are very closer enough, and they are forming some of the patterns. We can say that so the relationship between the variables or the features is it's something close, and we have some of the strong relationship between them. So in this case, there is high correlation. So we can say it as the multicollinearity. To make you more clear, I can say an example. We can consider the example of we have to predict the house price predictions, and the input features are house size, and the another feature is number of the rooms, and the output is we have to predict the price of the house. Okay, but in this we have the multicollinearity concept. So how? So in the input features house size and the number of the rooms. So this both features have the strong correlation. How means so when the size of the house increases, at the same time the number of the rooms will be increased, right? So like when the house size increases, we can actually extend our rooms, right? So from 2 bhk to 3 bhk, it's like that, right? So the both have the strong correlation. So in this case, we can say it is a multicollinear. It has the multicollinearity in the data set. So in order to handle that efficiently, so if we have that collinearities, and then the coefficient of both the features will be unstable, right? So in order to handle such cases, we can use the ridge regression. So what it does is it adds the penalty like L2 penalty, which actually regularize that coefficients and also makes our coefficient more stable and to help to perform our model in more generalized way. So that will be done by shrinking the coefficient towards the zero. Not it won't eliminate that. It actually reduces the coefficient towards the zero using the L2 penalty. So it helps us to solve both the regression and the classification problems. When we have to use the supervised learning ridge regression algorithm in the such cases, when we have the multi-hole linearity in our database, or if we feel coefficient estimations are very unstable, and we need the better generalization model for our cases, then we can use it. So you can see another graph as well. So where it's a simple example how the ridge regression, linear regression, and the lasso regression is actually uh, plotting the projection line for the same data. So how different it is. Then I like to explain the mathematical formula for that. It is very simple. Just understand the concept. So here the residual sum of square formula. So this ridge regression uses this formula, but by adding the shrinkage penalty to that formula. So as I said, by adding the L2 penalty, they are actually handling the multicollinearity and the prevents the overfitting by shrinking the coefficient towards zero. So this actually done using this formula behind it, the math formulas and the intuitions is this is actual intuition. Um, so using the formula, uh, all the calculations will be handled in order to provide more generalized model. So in the similar to this ridge regression, we have lasso regression and the elastic net. So which will be in the all are the regularization techniques. So ridge regression is actually used to reduce the overfitting and also handles the multicollinearity. And performs L2 penalty. The lasso regression uses it to perform the feature selection and uses the L1 penalty. And the elastic net is a combination of the both L1 and L2. So it is more all similar, but the performance, the use cases, and the methods will be different. We are going to see about the stochastic gradient descent algorithm, so which is actually the optimization algorithm, which will be used both in the machine learning and the deep learning concepts, and especially which will be used for the most large data sets. So it will be performing well for the large data sets. So it's actually mostly used for the large data sets. And the primary goal of the stochastic gradient descent is to minimize the loss functions. So loss function is nothing but the measure of the error which will be predicted, which will be generated from our model. Okay, so this is the general concept of that. And some of the benefits of the stochastic gradient descent is it can be performed with a more efficiency, and also can perform in a real time, it perform well in the real time data operations and everything. And the disadvantage is noise update. Why this noise update is happening? Because like in a normal gradient descent, we have to see before knowing the why is the noise update happening, the gradient concept. So in the gradient concept we know. So in order to reduce the loss function, it is actually find out the increasing um, direction of the error where it is increasing. So how it increasing the errors, where the errors are arising in the model. So it will find out that first, and then opposite direction, it will update the model parameters and try to reduce the errors and to up to the minimal cost of the weight. So where we call that point as a local minima. So this is general gradient function, how it works. So in while this working in gradient descent, it will actually the gradient local minima, reaching the local minima will be in the one direction, but in the stochastic gradient descent, it will be little fluctuating, but it will reach the point, but it will be little fluctuating as per we are updating the model parameters, right? So here we'll be updating the learning rate. So if we are actually updating the learning rate too far or too less, it will be little fluctuating. So the model architecture, it's like that. So because of that, we'll get some of the noise update. And also, as I said, the learning rate will be the hyperparameters is too sensitive. We have to give the right learning rate in order to achieve the local minima. So or else it will be more fluctuating. So and as I said, stochastic gradient descent supports both the regressions and the classification problems. How it works is it actually finds the initial weight and the bias for the model. Then algorithms iterate through the each process for using the getting the training samples batch by batch. So it will get only the subset of the entire training data. Then it will calculate the gradient calculations, which is a gradient of the loss function. So gradient of the errors, how much measure of the errors, and it will be update the parameters in the opposite side of the gradient in order to reduce the error, and at the end it will actually reach the global minima. So in the image you can see that if we have to consider, if we are adding the five features, so for the five features also it will compute in the same way, so that we can say the five features have the gradients, its own gradients, and also it had find the local minima and the global minima for each of the features. So this is how the SGD works, and it's actually more a super problem for when we are dealing with the large data set. And the linear discriminant analysis, LDA. So the linear discriminant analysis is actually the powerful machine learning technique which will be used for the classification and the dimensional reduction problems. So in this, it's actually used to find out the best linear projection line between the classes. So it's best for the classification problem in order to separate the multi-classes in a appropriate and the optimal way. Okay, so how it does is actually it actually finds out the ratio between the between class variance to within class variance. So it will actually maximizes that class ratios, and it will find out the projection line, so where it actually best split the multiple classes. So we can say that in this example, so before LDA we have the cluster of the circles and the triangles. After LDA it got the projection line, right projection line, and it has separated the circles in one part and the triangles in one part. So this is how the linear discriminant analysis, LDA, works. And the key uses is classification, dimension reduction, and the feature extractions. So let me tell you how it will works. For first it will actually find the mean and the covariance. Means like all the classes, each classes, it will find the average, and it will find how far the classes were spread out in the particular graph. And the secondly, it will compute the particular thing within class and the between class scatter. So within classes, so within the particular class, how far the pointers are there. For example, let me consider, so within the a circle class, how far the both the points are there. So that will be calculated, that is within class. And the between classes, so between the both the classes, how far the points are. So it will be considered like between the circle and triangle, how far. So this will be the between classes, this will be the within classes. So these 2 points will be computed, and by using this 2 points ratio, they will find the new axis using some of the math like eigenvectors and the values, and they will find the new axis line. And in order to find the optimal one, they will actually maximize the between class and the within class ratio, and they will find the new optimize the projection line. After finding that, they will transform the original data into the new one. For example, so after finding this projection line, they will transform this data into the new one, so that they will put all the circles and the triangles in a different part, and it will be more optimal to separate both the classes. So this is how the LDA works, and LDA is actually comes under the supervised learning. And if you want the similar concept in unsupervised, we have another one called PCA. So it will maximize the variance of the whole set, and LDA actually maximize the distance between the groups. So these are the similar concepts which I like to tell. So that's all about LDA. Then the quantile regression. So this is another powerful statistical method. So we can compare with the linear regression. So in and we can learn this. So in the quantile regression, so it uses a specific quantiles, like it will find according to the median instead of finding with the mean. So in linear regression, we'll find the we'll use mean uh, in order to find the make the predictions for the regression problem, right? But in quantiles, we use median instead of finding the mean for the regression problems. Here we have find median and the 25th percentile and the 19th percentile. So for example, we can consider that quantiles is actually 50th percentile, 10th percentile, 20th percentile is actually, it divides the uh, particular data set, and it helps to find with all the lines. For example, let me say in linear regression, we have only the one line. So if you wanted to find average for the regression problem, after computing, we'll only go to one line, this mean. And but in the quantile regression, we have the median, so that it will consider the median line on also 75th percentile projection line, and also the 25th percent projection line. So it covers most of the data, so that it can efficiently handle the outliers of the data as well. So outliers in the sense which is actually the far uh, from the median point, so that if the data is far from the median point, we can consider it as outliers. So it will handle that also. And also in this quantile percentage, we can't, it's actually the dynamic. So we can specify this 25 or 70, if you want 90, 10, all those values you can modify using the quantile parameters. Then, as I said, it used to handle the outliers and heterogeneous effects. So heterogeneous effect in the sense, yeah. So if, for example, if we consider they are giving in the company, they are giving the 5% salary hike for all the employees, but in the all the employees they include the higher salary employees and also lower salary employees. But if they put at the 5% hike, the hike salary will be not different. It will be like based on the salaries of the employee. As the higher salary employee will be getting the good getting the amount which will be, of course, greater than the lower salary employee, even though the percent is same. But according to the base salary, it will be calculated, so it will be little bit high. So in this kind of case, we can consider this effect as the heterogeneous effect. And coming to the loss function, which is the calculations of the quantile regression. So in linear regression, it will be calculated by minimizing the squared errors. But here in the quantile regression, it will be calculated by minimizing the sum of absolute errors weights. So it will actually calculate by minimizing the weights of the sum of the absolute errors. So this is how it will work. Okay, now I will like to explain the coding part for all the four algorithms. So regression. So in the regression, I've taken the regression problems and solving regression problems using regression and the quantile regression. And for the classification problem, I'm considering the SGD classifier and also the LDA, linear discriminant analysis part. So for the regression problem, I am taking the data set which is the insurance charge prediction. So here we are going to predict the insurance charges. I'm loading the data set and I'm converting the categorical into the numerical data set. Here I'm actually converting the categorical column gender and the smoker into the number. So as the ML process the number numerical values when we are computing with the algorithms, then afterwards I'm splitting the input output. Here the output is charges. Other than that, all are input. So I'm storing it in independent variables and other output as a dependent variable. Then after that, I'm splitting the test and train data splits set with the ratio of the 80 to 20%. And after that, I'm actually standardizing my model in order to scale it. And I'm actually here creating the model using by inputting the reg and also reg with the alpha equal to 1.0. So I have said, right, the penalty which we will be adding in order to prevent the overfitting and the multi collinearity. So here is this a parameter which used to do that so far. So then after that, if you wanted to see the coefficient intercept, we have the attributes particularly for the ridge regression. So you can see that. So what are the coefficient the model is trained upon for predicting the output. Then I'm actually predicting the output by for the test set of my data, and I'm evaluating it. So I'm getting the 79 percent. So then we have the rich CV, which is the rich cross validation, which is the built-in um, library for the rich. So it has a built-in cross validation technique. So using that, I'm actually applying the different alpha, which is actually the penalty values, and I'm actually running my model. After that, I'm predicting and I'll also evaluating the model. So it is actually again the same accuracy, 79%. There is no changes. And I'm checking the model is overfitting or underfitting. No, it is actually the good model. So this is actually the ridge regression. So which I got the accuracy with the 79%. So next, let me check for quantile regressor. Here, same. For the regression problem I'm taking and the insurance charge prediction model. So I'm putting the data set, converting the categorical to numerical input output split and the test train split and standardization and the model creation. Here I'm using the grid search CV as the quantile regressor doesn't have any inbuilt cross validation technique. So here the parameters I'm setting is quantile, alpha, and the solver, and I'm running the model. And after prediction, if I evaluate, the percent is 74. Uh, I've checked the overfitting or underfitting model, so it is actually performing moderately. Then the model actually initially it is got underfitted, but after reducing the alpha value, its performance was increased slightly. But I like to conclude that Ridge is performing better than Quantile as it is accuracy 17. So this is about the regression problem. So let's move to the classification problem. So let me start with the stochastic gradient descent for the classifier. So for classification problem, I am considering the social network ad data set. So here, as I said, the data set will be imported, and here also I'm converting the categorical data gender into the numerical one and removing the user data as it is unnecessary for the prediction of model. Splitting the input output and splitting the train and test in the same ratio 80-20. After that, I'm standardizing my model and creating the model with the default parameter for the SGD classifier with the loss, penalty, alpha, max, iteration, and the learning rate optimal. So all of the default parameters. After that, I'm actually just seeing the coefficient intercept and predicting the model and evaluating the performance using the confusion matrix as it is a classification problem. Here, I have getting the accuracy of the 82, but the overall performance is good, but the class 1 precision is 0.64, so which is a little bit lower, but we can uh, consider it according to our use case. So for the finding the social network problem statement, and the model is actually good, appropriate fit. And let me see for the linear discriminant analysis, a classification problem, same, do the data set and conversion and input output split, restraint split. So here I am again standardizing my model, then the linear discriminant analysis with the same default parameters. Here are using the parameter solver SVD, then the coefficients and the model prediction. So here I'm predicting the model and evaluating using the confusion matrix. So here it is performed really good, 91, and the overall performance was also good, but the default is 77, but it's actually far more better than stochastic gradient descent, and also model is actually a good fit. So I'm considering for the classification problem, my linear discriminant analysis is performing well, and for the regression problem, reg regression is performing well. So that's all. So I hope the explanation for the four algorithms was clear. And thanks for listening. Thank you.